Welcome back. This is a teaching sheet on sound, and then I have some questions on the back that I'd like you to try on your own. So sound is one of the manifestations of an energy wave that passes through a medium. So air is a medium, or water is a medium, because you can hear underwater if you're swimming in a pool or whatever. So some kind of a medium where you've got molecules that are all separate but are close together. So most in air, it's not an excellent medium for sound, believe it or not, because the molecules are so far away. But if you've got kind of floaty around air molecules, and you have an energy wave that's shoving them together, okay? So look up here for a second. If you've got air molecules that shove together, so let me put that in red, okay, up here where they're all compressed, it's shoving together, it kind of acts as a spring. Those molecules don't like to be shoved together. They don't like high pressure. High pressure always expands into low pressure. So just like the wind blows from high pressure to low pressure, so this small compression of air molecules in front of a sound is going to shove together like a spring and then bounce back. When it bounces, it will shove the next molecules ahead of it into a compression, and then it will relax into a rarefaction. So you have a compression here where it's all packed, and then you have a low pressure area called a rarefaction. The high pressure is analogous to the crest of a wave where it's all shoved together, and the rarefaction, where there's low air molecules, is a trough. And so what's happening, since it's shoving the next molecule, shoving the next molecule, shoving the next molecule, the wave will travel in a straight line to the ear. The ear has an eardrum, and the eardrum can set up a sympathetic vibration with the wavefront that's coming up. And there are 3 bones attached to the eardrum. So if I have an eardrum here, I've got the incus, the malleus, and the stapes, which are little tiny bones, very, very small, called ossicles in each ear. And then it's attached to a cochlea. The cochlea is kind of a snail-shelled tube with some fluid in it, and also some very small hairs that are all attached to your nerve, to your auditory nerve. When the last bone kind of slugs in, makes kind of a punch into this fluid-filled sac, it jostles the fluid, and depending on the frequency of the sound, the fluid will either go farther or not as far. It's a big push or a small push. So the farther that water sloshes around on the inside of that snail-shelled cochlea, the more cells that are attached to your nerve will impact, and you'll hear it as a high frequency or as a low frequency. Okay, so a speaker will imitate a sound by an electrical signal that's now shoving against the usually paper of the front, and then as it shoves the air, it'll allow that air to form a compression very similar to what it would have been when it was originally made. Now the frequency of the pitch is based upon how fast that vibration originally occurred. Whatever the oscillator, whatever was vibrating that made that sound, and so it will shove the air back and forth at a certain frequency. Those frequencies are interpreted by the cochlea as being high frequencies or low frequencies. So some of them are subauditory. You can't hear them. For instance, 10 hertz, most people cannot hear 10 hertz. Or if they can, it's just really, really low. It's almost like they can almost hear it. 20 hertz would be, say a really low rumble of thunder, very, very far away. When you get up to 10,000 hertz, that's about normal hearing. And even older people many times can hear up to 10,000 hertz. Young people, children, of course, animals can do this too. Dogs have a different ear, and they will hear higher frequencies than people do. But say teenagers would many times be able to hear up to 20,000, maybe even a little higher than 20,000. And you can kind of tell that. So the amplitude or the loudness is not analogous to how fast these waves are traveling, but how high that they travel away from the middle point. So the higher the amplitude, the louder that sound. If we're talking about light, eventually, you'll see that the amplitude would be analogous to brightness or intensity of that light. So this is measured in decibels, and a decibel is on a logarithmic scale Okay, so it's not linear, it's actually logarithmic. It's going to every bit louder, it's going to get even louder. So every notch, every decibel, okay, or every 10 decibels, I think it's in a 10 scale, every 10 decibels is actually twice as loud as the previous. Okay, so 30 decibels is going to be twice as loud as 20 decibels. So for instance, something that's really, really loud, 200 decibels could cause death. You could actually, the pressure could actually implode your head, believe it or not. Pretty awesome. Okay, I hate imploding heads. So frequency is pitch in sound and in music, and amplitude is loudness. Okay, so last part on this page is the speed of sound, and the speed of sound is different in the different mediums. So in air, which is really loose, it doesn't go very fast. It goes about 340 meters per second. If you have something like a steel railroad track, it travels almost 6,000 meters per second. Elephants have really, really, really large feet and can hear vibrations in the ground and can know whether there's another family of elephants 2 miles away. You couldn't do that. You could not hear from your feet in the ground, but the ground is vibrating. If you've got elephants across the hill, they're vibrating, and that vibration can be picked up by the elephants. So it depends, again, on what it's traveling in terms of how fast it is. If you remember, we've done this a couple times. The speed is going to be equal to its frequency times the wavelength. So if you know the wavelength in meters and you know the frequency in hertz, and hertz, remember, is nothing over seconds, then if you were to have meters times divided by seconds, you'd end up with meters per second, which is your speed, velocity. Okay, so they're going to ask you some questions. I want you to try your best. Ask me, I can help you. I make a great lab partner. All right, thanks.